Alright. Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera to everyone. Now is another video recorded for a new chapter which is molecular orbital theory. However, it's still in the chemical bonding. Previously, we studied the VACPR theory to study, to determine the geometry of a particular molecule. After that, we studied the valence bond theory. We try to hybridize, identify the hybridization of that particular molecule. But now we will discuss further the chemical bonding by using molecular orbital theory. Along the way, you should identify what is the reason to study the molecular orbital theory. So, molecular orbital theory is describe the valence electron in the molecule using molecular orbital. In the valence bond theory, we describe the valence electron by using atomic orbital, the overlapping of atomic orbital. But now we describe the valence electron using molecular orbital. So in the previous topic, we just focus on this part, the atomic orbital overlapping to form chemical bonding. But for this molecular orbital theory, we expand it further to this part. Molecular orbital theory, it can be bonding and also it can be anti-bonding. So we start to discuss the molecular orbital theory using the simplest molecule. As you can see here, the hydrogen molecule, the overlapping of 1s atomic orbital, 1s atomic orbital with 1s atomic orbital, it produces two molecular orbital, the bonding molecular orbital, anti-bonding molecular orbital. The number of atomic orbital, this is one atomic orbital, two atomic orbital, the number is 2, is equal with the number of molecular orbital formed, bonding and anti-bonding. So we focus a little bit on this diagram. If we are asking to draw the energy molecular diagram for molecular orbital for this molecule, as usual, we should have energy axis. This is energy, and then we have the atomic orbital. Because of this is hydrogen, it should be 1s, 1 plus 1s, 1. So this s orbital overlap with s orbital to form two molecular orbital. First is bonding molecular orbital and anti-bonding molecular orbital. So the shape of the molecular orbital is slightly different compared to the isolated. In a bonding molecular orbital, it means addition, 1s plus 1s. So we added the atomic orbital, it becomes symmetry. However, for the anti-bonding molecular orbital is a subtraction, 1s minus 1s. So for the anti-bonding, is a very special if have not in the middle. This is not. So the bonding, the addition, it become like this. The anti-bonding, the s orbital will be in symmetry. The electrons will be further away from the node region. This why, as you can see, before antibonding is a round in shape, but in the antibonding molecular orbital, is look like a little bit oval. Okay. So another information from this diagram is labeling. This is a bonding molecular orbital. The bonding that form is a sigma. Why is sigma? Because uh, 1s, 1s. Hydrogen is like this. This one is a sigma. Sigma 1s. So for the anti-bonding is a sigma. Anti-bonding, they have a star on the top. Anti-bonding star 1s. Okay. All right. So just now we study a little bit on this sigma, sigma. Now we have a px, px. Also the px, px is the sigma bonding. This px, px also sigma. The px orbital overlap head to head or end to end. It's the same thing, end to end. To form sigma to p or anti-sigma to p. So this is a px px, same. This is energy axis. Px px for the bonding. The shape is like this. The in the middle, uh, they have electrons, higher, greater, or a greater electron density. When this one is overlap, so for the bonding, because of the addition, the electron density become greater for the bonding electron. However, for the anti-bonding, is a subtraction. They have not inside. So the shape, the electron will be repel or repulse ataupun repulsion, mengalami repulsion. So this why the shape is unsymmetry. Most of the electron is further away from the node. Okay. So for the PY, we know PY is pi component ataupun pi bonding. So the PY for the bonding, it become like this, or you can draw like this as you did previously. You just connect them using a dotted line to form a pi. However, for the anti-bonding, they have not in the middle, so the PY will be repel away from the knot. This is why it look like butterfly. So this is PY or sigma 2p bonding or sigma star anti-bonding molecular orbital. Okay, so this one is description or explanation regarding the bonding and also anti-bonding. If you analyze the diagram just now, the bonding molecular orbital is the addition of atomic orbital, in which the region in the middle overlapping consists of high electron density between the nuclei. Meanwhile, for the anti-bonding, it is subtraction. It means that the region in the middle, they have zero electron density. Zero electron density is a knot between nuclei. And also you find out the bonding molecular orbital is lower in energy compared to the isolated atomic orbital. The antibonding also, is higher in energy compared to the isolated atomic orbital. This one. This bonding energy lower energy than this antibonding higher energy than this. Okay. So because the electron in this molecular orbital is strongly attracted to both nuclei. Let's say we have this this px. This electron, valence electron, will be attracted to this nuclei. This electron will be attracted to this nuclei. The electron is negative charge. Electron, the negative charge. Nucleus in nuclei is a positive charge. This is why this electron attracted to this nuclei, this electron attracted to this nuclei. Even though they are attracted to each other, the electron also feel the repulsion. The nucleus also feel the repulsion. Why repulsion? Because they have a similar charge, negative charge, negative charge. So it repel. Positive charge and also positive charge, it repel. Okay, so in the bonding, the repulsion, electron repulsion will be reduced. This why this is the reason the bonding molecular orbital lower in energy compared to the isolated atomic orbital. For the anti-bonding, the repulsion increase. Either you use the electron repulsion or nucleus repulsion is the same due to the increasing in repulsion, because in the anti-bonding they have knot in the middle, so the electron will be further away. So it means it's showing the repulsion increase or higher repulsion. This is why the energy of the anti-bonding is higher compared to the isolated. When the electron occupy the orbital in lower in energy, so it's meant that we call it the molecule will be stable. The electrons occupied the orbital at higher energy, causing the molecule less stable. Okay, so this molecular orbital is stable. This is less stable because this is higher energy. That one is lower energy. All right. So for this one, nothing much. This one is we try to explain the formation of molecular bonding molecular orbital in anti-bonding molecular orbital using wave. Wave is look like in the physics. Masa kita belajar fizik dulu, kita ada wave function. So you can read if you wish. If you don't want, we just ignore. What I want to show to you is this one. For the bonding molecular orbital, as we know, bonding is additional. So we added the wave. So the added the wave, so it increased the amplitude. But if we have anti-bonding, it should be cancel each other because it's subtraction. So this is the analogy of formation of bonding in anti-bonding for molecular orbital from the respective of physics. So this one, if you want to know, you can read. If you don't want, you just ignore. You just lupakan. Okay. So again and again in organic chemistry, we draw a lot of energy molecular orbital diagram. All right. So the energy level diagram of molecular orbital for any molecule quite similar. So we started with the simplest molecule. So in each molecular energy diagram, it have proxy Y, which is energy, and we have these three things. We have atomic orbital of the first atom and atomic orbital of the second atom. So in the middle, it's not atomic orbital, but it is molecular orbital of hydrogen. So as we know, the valence electron of this hydrogen is one. So each atomic orbital is 1s1, 1s1. For the molecular orbital, as we know, the molecular orbital, it can be bonding and also it can be anti-bonding. So in this case, the bonding is sigma 1s, anti-bonding is sigma star 1s. So now we try to fill in the electron in the molecular orbital. Because of this atomic orbital is one electron, this is one electron, 1 plus 1 is 2. That's why we distribute, 1 plus 1 is equivalent 2. This is why we try to distribute the 2 electrons in molecular orbital. So, of course, we complete the lower energy level, 1 electron, second electron. But if we have another electron, for example, 2 electron to 2 electron is 4. So we complete this orbital first, 1 and 2, and then 3 and 4. All right. So the electron occupied the bonding molecular orbital. We call it bonding electron. Because the sigma 1s orbital is lower in energy, is compared to this isolated atom or isolated orbital, the hydrogen molecule is more stable compared to this separate atom. This hydrogen stable compared to separate. So electron configuration for molecular orbital slightly different is compared to the electron configuration that we write before. Before this, in electron configuration is like this: 1s1 or 1s2, 1s2, 2s2, or what? 2p, 2p6. This is the way we write the electron configuration. But the electron configuration for molecular orbital, we should tell the type of bonding as sigma or pi, but in this case, we have a sigma 1s. How many electrons? Sigma 1s, 2 electrons. So sigma 1s, 2 electron. If we have this anti-sigma containing another electron, we can continue. So sigma star 1s, how many electron? 2 electron. So this is the way to write the electron configuration for molecular orbital. Okay. So the information in the pink box is the description, the principle. How do we fill in the electrons? So if for the molecular orbital, we fill it with the electron. The molecular orbital fill it in order of increasing energy. We call it above principle. So we're gonna to fill in the molecular orbital with lower energy first, and then follow up by the higher energy. In the molecular orbital, maximum is 2 electrons with opposite spin up and down. We call it exclusion principle. The orbital of equal energy are half filled with spin parallel before any of them is completely filled. This is Hence rule. Yang this one dia lebih kepada p orbital because we know p orbital is 3 boxes. P orbital is 3 boxes. Any molecule have a p orbital, so the molecular orbital akan berpecah kepada 6. Kita ada sigma, lepas tu kita ada pi, and then kita ada inti sigma, and also kita ada inti pi. So the orbital equal energy, for example, this one, py, pz, pz. So the spin kita buat parallel dulu. Let's say 1 electron, second electron, parallel. And then baru kita buat spin down, spin down. Itu yang maksudkannya dengan Hence rule. Alright. So now we moving forward another example of molecular energy level diagram using the helium, He2. After hydrogen in the periodic table, ujung sekali kita ada helium. Tadi kita dah buat dah hydrogen, we understand. Now kita buat untuk helium 2. So the molecular orbital energy level diagram of helium 2, we know helium is 1 s2. So this is the energy. The atomic orbital of helium, the first helium is 1s2. The second helium 1s2. So in the middle is the molecular orbital of He2. So sigma 1s and also inti sigma 1s. So how do we fill in the electron? Fill in the electron in the molecular orbital because it's 2 electrons, so we have to distribute 4 electrons. 1, 2, 3, 4. All right. Wherever there is equal number of electrons in bonding and anti-bonding, equal number of electrons in bonding and anti-bonding, the lower energy of bonding molecular orbital will be offset by the higher energy of anti-bonding. So this helium He2 basically is unstable and no bonding. No bonding meaning that the bonds does not exist. So molecule ni sebenarnya tak wujud. Walaupun dekat kertas helium 2 macam boleh buat, tapi in the laboratory during the experimental whatsoever, we couldn't form the He2 because the bond order no bond. So how do you know there is no bond form? Macam mana kita nak tahu tiada ikatan yang terbentuk? So one way is kita kena kira bond order. So this is the formula of bond order. Bond order is half multiply bonding electrons minus anti-bonding. So only the molecular orbital theory can tell how many bonding electron, how many anti-bonding. So kalau kita patah balik ke sini, macam mana kita nak buktikan this is no form? Kita kena kira dia punya bond order. So as we know, bond order is half. How many bonding electron? This is 2 bonding electron. And this one is 2 anti-bonding electron. So the bond order is 0. When it's 0, it meaning that no bond. Molecule does not exist. Kalau kita patah balik yang hydrogen tadi, kita pun boleh kira dia punya bond order. Kita nak tengok sama ada hydrogen ni boleh dapat ke tak in the lab. So bond order is half. Bonding electron is 2. Non-bonding supposedly is 0. So bond order equivalent to 1. So hydrogen H2 is possible to be formed because the bond order is 1. Okay. Right. In the molecular orbital theory, the stability of covalent bonding is depending on the bond order. The higher the bond order, the stable of the molecule. The bond order is integral. It can be 0.5. Any number, it can be 1 depending on the molecule. It can be 3 or it can be 4 whatsoever. As long as number, as long as not 0. 0 is no bond, no order. The molecule does not exist. A bond order greater than 0 indicated the molecule form is stable than the separate atom. A bond order of 0 meaning that no bond exists. So the species does not form. The higher the bond order, the stronger the bonding. Alright. It's an example because hydrogen molecule has 2 bonding electrons and 0 anti-bonding electron, and then we include in the formula of bond order, we calculate the bond order is equivalent to 1. For the helium molecule, He2, the 2 bonding electrons with 2 anti-bonding electrons, so the bonding order is 0. When the bonding order is 0, no bond exists. All right. So generally, bond order of single bond is 1. Bond order of double bonding is 2. Bond order of triple bonding is 3. Okay. So we can use the bond order to discuss or to describe the star stability. To describe either the molecule or ion stability. Okay. So in this particular example, it asking you what is the bond order of He2 plus. Would you expect this ion to be stable compared to He2 molecule? So kita kena kira dia punya bond order. Nak kira bond order, you kena buat dia punya molecular orbital theory diagram. Pada situ baru you boleh tahu how many bonding pair, how many anti-bonding electrons. Before we draw the respective molecular orbital diagram for these two ion and molecule, you kena faham dulu apa yang dimaksudkan dengan He2 plus. Bila ada plus ni, maksudnya kita remove one electron. Kita remove electron. How many electron? Kalau ini plus, one electron. Kalau kita ada He2 plus, maksudnya kita kena remove 2 elektron. Okay. So, kita draw dulu the molecular orbital energy diagram for helium. This is the molecular orbital energy of helium is we explained just now. So kalau kita nak buat He2 plus, maksudnya kita kena buang satu elektron. Bila kita nak buang one electron, we should remove the electron from unstable orbital. Unstable orbital maksudnya adalah stable yang mempunyai energi yang tinggi. So kita kena buang daripada sini. Okay. So dia akan jadi macam ni lah. Maksudnya kita dah buang satu, tinggal satu. So baru kita kira dia punya bond order. Kalau bond order for He2 adalah half 2 minus 2, it becomes 0. Bond order of He plus is a half 2 minus 1 is half. Okay. Andai kata dia kata He2 plus, so maksudnya ni akan jadi kosong lah. So bond order of He2 2 plus, it become half 2 minus 0 is become 1. So if it asking in term which one is more stable, kita tengoklah. The higher the bond order, the stable the molecule. So between this He2 dengan He2 plus, the bond order He2 plus is more stable compared to He2. Alright. Okay. I think I stop here. On the next video, we will continue with this subtopic, molecular orbital of second row of homonuclear diatomic molecule. What is the second row? This is the second row. Just now we covered hydrogen and helium. Next video we will cover the second row from lithium until fluorine. Alright, so it's enough for this video. We continue on the next video. Thank you very much.